My name is Artem. So, hello everyone. So, I am working on Realm, part of the team. So, we are currently a group of three. That's we, including myself, who contributed to Realm at NVIDIA. So, and I'm just going to be the messenger today, talking about the things we have done so far since the last Legion retreat. So, yeah, let's just go with it. So, the outline is going to be simple. So, I'll basically just walk you through the new usable things that we have done and working on. Going to be the mix of both. So then we'll together look at some of the improvements, more like runtime internal that we have worked on and as well as working on currently. And then we'll basically look at the ends of the robustness. So kind of like, very simple outline. There's some semantical grouping over here, maybe, just on the runtime general features that are there that are new to Realm. So networking related and also like the GPU related. So basically we'll walk over them through this particular order. Now, I think basically one of the objectives I want to talk about is to adding the Realm tutorials. So I think we've done it like a while ago. One of the objectives is that we want to be in a position where we can safely onboard the new customers, for example, for Realm, as well as advertise the programming models. So, and that is basically our first step to add some kind of documentation. So for those who aren't familiar with Realm, to be able to actually understand how to write Realm programs. So there are basically 14 of those. They are structured in a way that you can work your way from writing a simple hello world program, then learning about some basic concept of how to work with instances and index spaces, and then like eventually make your way to some more advanced features like a subgraphs, completion queues. So, and hopefully we'll be able to understand like what's happening, how to actually write those programs. So now, if you already use those and kind of know about this, let us know how we did. If you don't and have a use case, please go ahead and take a look. I mean, we're always looking for feedback and try just to improve on those. Right. Now, we're working towards basically addressing and improving on Realm profiling. So I think the feedback was always that there is not much visibility on what's happening inside. And we're sort of like, trying to take a step forward with this. One of the things that we are currently actually adding, Mike was actually kind enough to do that, like a proof of concept. There is so-called the profiling interface in Realm that already exists. So you can actually enable that. For example, if you want to be able to understand like when you create instances, when it was created or deleted. So, and basically the P-Realm, it's a wrapper around this interface, our public interfaces that basically will enable that. And you'll also handle the profiling data. We'll make sure that it's compatible with the Legion prof. So basically, this is our take on this. So Legion prof already been there. So quite an effort has been put in developing, designing and developing this. So we kind of like, want to be able to build on this. And that's like one of the directions right now we're currently looking at, as well as we're essentially looking at basically putting more information across our pipelines, networking layers like inactive messages, for example, and do the general improvements for very existing things, for example, improving the profiling of the GPU kernels by QPI, et cetera, et cetera. So we kind of want to take a stronger stand on this, and maybe deliver some more complete solutions somewhere like early next year. Okay, now in this same context with the usability and sort of like, the legacy way was always to configure Realm through the command line. So there was like a zillion of arguments you have to do. Not always the most ergonomic and flexible way. So, and Way was the one who actually designed and released the interface basically to programmatically configure Realm. So basically like on the right-hand side, you could see here is that how you would do that, waiting whether you have, for example, support for CUDA, and then, set up some of the properties like a number of GPUs and size up your frame buffer memory. So if you're not familiar with this, I'm pretty sure like we will be happy actually to take all the questions offline and to walk you through how it actually works. Now, there is a concept of the processors within Realm, like a latency processor, which is CPU, or throughput processor, so, or the Python. So if you essentially running your task on the GPU processor, on the Python processor, but you can have a combination of both. So now Corey is doing a fantastic job by actually leading the design, make sure we actually change this concept to a more fluid one by essentially allowing the processor to be like, composable. So for example, you can have features like a Python and plus GPU. So yeah, it's pretty much right now in the design stage. So there's more details, for example, on this link. And as well, I think we'll be happy to take all the questions offline if you have on that as well. And there's basically the code snippet how it showed that, but I'm probably going to skip it. Okay, so slightly orthogonal feature that we added is, and I think Mike talked about this, is with the tuple problem is that today when you create an instance for the realm, you specify the data layout, and it's fixed. So you can change it if you want to be able to use allocations. So, and it's only true with this with the restricted feature. You can now basically on the fly change the shape of your instance, for example, to another one, or you can actually choose it to be a kind of like a pool, and you can split its one into several smaller instances, each individual data layout. So basically, that's all about. So there's also more detail about like what exactly it does and what are the issues that it actually solves. It has been true for a long time that Realm was basically like working with a GasNet, in more precise GasNet EX as a networking backend. So one of the issues with that is that's not ABI stable. That also makes a Realm binary is not quite portable because you have to compile the GasNet EX for a particular conduit. So usually on a client machine. So in the way to address that, the way we did is basically introduce this stable like FinABI binary within the Realm and moved all the dependencies on the GasNet into the wrapper, adding the tooling for that. So this one you have to compile now on a target machine and in the shared library, and then we basically load it for you. That makes us kind of more portable in that regard. Okay, now the UCX, it's gonna be, I think it's already known that we're supporting UCX. I just like put a slide there just to call it out. That right now when you're building in one realm, you can actually choose whether you want to be able to work with the GasNet EX or UCX. There's also MPI, but it's like less supported. You can actually use both at the same time. And one of the objectives for us was to be able to actually add the UCX is that NVIDIA is the main contributor to the UCX. And for us, networking is very fundamental. So we want to be able to have an access to latest hardware software features. And basically, this is our answer to this. I'm not going to cover, like, for example, what would be the difference where you would actually want to prefer to use the GasNet, and not the scope of the slide. Worthwhile to say, though, I mean, there's some different design principles that has been put in the UCX, for example. It can enable us in Realm future for some of the features, such as elasticity or, for example, fault tolerance. Okay. Let me just move on. There's a slide about collectives. So I want to actually move it in the end, but I decided to put it actually still here. So there's some initials right now in discussion that want to be able to add the layer of collective operations in Realm. So, and we're trying to achieve several objectives at a few places, for example, inside Realm, where we basically, using the point-of-point communication to implement the collective operations, for example, do the broadcast. And we want to be able to actually do it more efficiently by lowering that some library that can do it topology aware, for example, as well as, for example, for the legate, that today depends on the MPI and for the collective operations, and hopefully, for example, offering that to them, we can free them up and have to depend on the MPI as well, and simplify the deployment strategies. So I think it's pretty much the fluid design right now. So we definitely sort of consider moving forward on this. Unclear what shape it's going to be, but I think the main objectives that we have is that it has to be a consistent extension of the Realm programming model. So we wanted to make deferrable. It has to be cross-platform and also topology aware, basically. Okay, now switching gears a little bit to the CUDA. Essentially, we added some of the APIs interfaces to right now to query the Realm managed task stream. So for example, and disable the CUDA context scene. So kind of like a little background on this. When you're running your task and launching your work on the GPU, you essentially have a completion event that signifies that the task has been done. So for Realm, for the runtime to say that a task is done, it has to know that also all the work launched on the GPU has been completed already. So now, if you're having the hijack enabled, so that will forces all the work on the Realm managed streams. So and then synchronization becomes easy. If you have it disabled for some reason, we're actually moving away from the using hijack overall, you'd have to run a pretty expensive CUDA contexting in the end. So, and that's basically the API allows you to do. You can either get a stream and turn it off manually. You can use this task signature, which is basically stream aware. So they will be do it automatically for you. As well as we did some optimization. I think since CUDA 12.5, there is a way to be able to actually record an event on the context. So you won't have to do the blocking CUDA context sync, but you actually be able to get an event on when the work on the context, CUDA context has been completed. So it's also, the API is available on HIP. Okay. So that was the things that are more like user visible. Now I want to basically in the same way, I'll walk you through the stuff that we actually done in Realm. So there's not all the features actually here. Just like to be able to save it on time, I put the most important slides, I think. Right, let me just go with it. All right, so there's a 4 fairly low-level slides with the high-level pictures and relatively important to RAM. So bear with me, I'm going to actually go and explain it to you. So working with events and tasks in Realm is pretty fundamental. So, and we want to be able to scale as much as possible to minimize the overhead. And basically, on the slide, what you see is that when you're creating an event in Realm, you basically, it has an object. It needs an object to be able to do all different kind of tracking. So we have a data structure that's called dynamic table that basically has a single free list. So, and that's where you get the object from. So, and usually when there's a multiple processes, they want to be able to get this object, the access is serializes. So now they have a contention. So, in what we did is we essentially made all these processes to be able to actually reserve the range of object, basically, adding the second level free list here by removing and therefore reducing the contention from the global table. And that's kind of what you see here with one of our benchmarks that kind of, it does show the improvement in terms of like a scaling. So in the same domain, when event is triggered, so there are usually some kind of like a task or operation that has to be executed. So, and the way it's done is that we call it like event waiter list. So it's kind of like a sorted queue. Each processor would have to go and look to that. So now the Realm has this optimization called default spawn cache that essentially like, keyed on the event ID. It has a ordered range of tasks has to be executed. So basically just optimize that. So we looked at this and noticed few inefficiencies. So for example, there is some stale interest in the cache for already triggered events. So we did some optimizations by replacing the eviction strategy and also added some more heuristic to actually help to improve the cache efficiency. So in here, for example, in this graph as well, you see that it actually with one of our task queue bench from the regression test suite. Now, we're also adding the cache allocator. So kind of the idea is that roughly like 25% of all memory operations in Realm is allocating structs. So like 600 bytes is fairly large. So, and for example, on the global memory allocator, it usually falls on the default on a large object pool path. So now it's also create some serialization. So we added the cache allocator to basically mitigate that. With the subject of so kind of like available benchmarks, it's a mixed bag. So in terms of like performance, so we also disabled that, I think, for the time being due to like uncovered like issues with the memory consumption. But the work has been there, so we did some analysis on this, and I think we'll definitely going to revisit it sometime in the future, maybe even re-enable that. Okay, and the last slide here, but not least, we did some improvements to processor group. So basically, a processor group is like a logical representation of the group of processors. So like maybe if you will, like unified process. So basically, it will help you to manage and launch your tasks. So now it has a number, it maintains a number of the queues inside. So usually like one task queue per processor. So we looked at this, also noticed few inefficiencies, for example, because whenever it has to for loop of those over them, acquire the lock. And even if the queue is empty, you still go ahead and do that. So we're gonna add a couple of early checks on this, a few other improvements, and that basically graph shows that we also do get some performance benefits in our task rate scaling. Okay, I think that was it. Now, we also scaled the barriers. I think I actually talked about it myself. So the idea that you would use actual random barriers today to synchronize your work across the tasks, across the processors and nodes. So, and the idea would be that inside the barrier, it uses this point-to-point communication. For example, it has a precondition, and the ranks will actually send an active message like arrival. And when the precondition met, it basically will notify whoever is waiting on the other side. So, and that basically creates this all-to-one and one-to-all communication pattern, which is basically linear. So we did a simple thing, just replace the linear communication pattern with a logarithmic one by adding the reduction in the broadcast sheets. We kind of build them manually. You can set the radix at the runtime, and that's basically the graph that's showing you, and that we did, I think, on use a while back, that shows you the OG implementation has this linear kind of scaling, and then a couple of different variants that we had by, turning off only broadcast or broadcast with reduction. So that actually is consistent with our expectations. So, okay, I'll move on. So I think we're also looking right now at optimizing the subgraphs. So Mike and Rohan actually doing this work. So basically, the idea is that we have this subgraph concept that allows you to capture and execute the operations. So the interface is there, but there is no optimizations. at the moment, and we're essentially looking to put the optimization inside. So, for example, to do some cheaper event representations or lower actually the part of the realm subgraphs into the CUDA graphs. If you're not familiar with this, there is a tutorial, basically a link that displays you what the subgraphs are and how to use them, and as well as that there's more details on this issue in what we are actually planning to do in this GitHub link down below. Now, we're also working on the hang detection. I think Wei is basically doing the job. On designing this, we kind of realized that large fraction of the bugs in the realm is essentially related to the hangs in some one way or another. And it takes a lot of 3 hours to be able to actually code it manually. So we're kind of building a native solution within realm that'll help you to answer the questions like whether you actually have a hang or not. So I won't be covering like how we're planning to design that. We have a design doc right now looking at what kind of hangs we're going to classify, how we're going to do that. But I'm pretty sure we can actually have an offline session, for example, if you want to know more about this. That is basically a work in progress right now. Now, I talked about that we actually added the UCX, but since then we also added some improvements to UCX and also adding the improvements to UCX. So basically, in addition to bootstrapping UCX with MPI, you can now bootstrap it with a PMIX, as well as we're looking at how to bootstrap MPI, for example, UCX, excuse me, on the cloud, on cloud when you don't have SRAM and MPI available. And there's a many more optimizations which I just left it out here. So Sam was like mostly the mastermind behind pushing for added UCX and optimization to the GasNet to the realm, excuse me. So yeah, and just basically just to call it out as well that we do work in this direction. Now we added the support for ARM64 architectures, basically improve the our enumeration for the ARM cores, decouple fixes for the technical platform. And that was part of our objective to be able to support the Grace Hopper, where the Grace is basically ARM-based CPU. There's a link that talks about this, what's the Grace Hopper actually represents. So I don't plan to go in explaining about this. But yeah, if you're interested in, there's a link. You can go ahead and read that. Now, we added the support for the CUDA map. For the CUDA map, essentially it's like a more powerful alternative to the CUDA malloc. It improves the locking contention within the driver during the allocation. It enables you like just more sharing capabilities, more secure, for example, compared to the CUDA IPC. So it's there's like a blog that Corey, I think, written a while back that talks about like what CUDA map is and what are the use cases it presents. So if there's something you're actually interested in, you can go ahead and also read this. We added the support for the shared memory. So now, for example, if you're running on a node and you have a couple of processes, you want to move the data, you don't really necessarily have to stage your copy through the intermediate buffer anymore. You have a joint link, which basically makes it faster, low latency for all your internet communication. So we have it now. You can basically allocate your system memory on a shared memory. And we basically added the support for CUDA multi-node fabric. So kind of building on the previous things I have discussed. So sort of like in NVIDIA terminology, we actually, that was part of our roadmap to support the Grace Hopper and to be able to support the multi-node NVLink. So basically the slide here showing you some of the picture, it doesn't necessarily show that it's multi-node, but let's assume that the left-hand side is it's basically one node with a Grace Hopper chip, and then the other is a second node. So now, for example, what Grace Hopper allows you to do, and in Realm what we support, for example, is that this on the left-hand side, let me actually use the mouse right now. You can access from the Hopper GPU the memory on a Grace CPU, and you don't have to do anything. So you don't have to do the CUDA malloc manage. You don't have to pin the memory. You have a memory coherency, which is guaranteed by the hardware through so-called the address translation service, like an ATS. So it will basically take care of the host and device page tables. So now, from very same Hopper GPU, you can now access remote Hopper GPU memory. And that's, for example, where we use the new API that's CUDA 12.03 has released, where we can basically CUDA create the handle. You can fabric enable that. We will send this fabric. We'll send this fabric handle to remote node. We will use the CUDA map to the mapping. To VA range destination GPU. And now you can actually basically have an access. So, for example, when you're hitting the virtual page, the driver will understand that basically it's fabric enabled, and they'll make sure that it writes the right place where the actual data lives. Now, from the same Hyper GPU, you can also now access the Grace CPU memory on remote nodes. So this is the concept which it's called like extended GPU memory, like in UGM. So for that one, you actually have to pin it. So, but it enables a set of also interesting use cases. For example, when you remote GPU memory, you actually have a data now. You basically can have an access and move the data through the NVLink. So at the NVLinks at the NVLink speeds. So and basically in RHEL, we will determine and if you are on a Grace on a multi-node NVLink capable system, it will basically enable add the DMA passes, and we'll make sure that you have the when you do the copy, you can actually have to utilize this pass to move your data between GPUs across the nodes. Now, I've talked about this CUDA DMA already twice. Probably gonna there will be the last time that I mentioned this. We have it done, so now it's inside. It's supported. So, for example, when you do the copy, let's say from GPU to GPU, and you want to move your data, in addition to the classical way using the CUDA mem copy in compute engine, you can now utilize DSM basically by launching the CUDA kernels. We have a number of special, the general purpose CUDA kernels that we've written. You can always add the specialize them if you want. So, and it's not going to be like a silver bullet. So, for example, for the large bulk transfers, the copy engine still going to be able to better saturate the bandwidth. But for the cases, for example, when you have lots of sparse small memory copies, like a sparse kind of pattern, or maybe you have some not particular CUDA mem copy friendly pattern, like a transpose or something with unusual stride, you have a high chance to be able to achieve a higher bandwidth going through the CUDA GMA. As well as that, for example, in the Grace Hopper, you have, for example, if you like on a system that has a support pageable access, we'll be able to actually use the CUDA GMA to do the host-to-host data movement for you as well. We support like batch-defined copies, transposes, fields, scatter gathers. And there is just a slide that shows you, for example, on a pre-CUDA GMA, how it would look like, for example, if you have this strange low triangular thing and you want to be able to copy the data. The GMA engine basically will unroll that, and you will result basically in the M number of the CUDA mem copies, each for each row. So, and now you can also do that with the GMA, hopefully in one pass, either doing the batch-defined copy, or for example, you can actually even use the scatter copy. And that hopefully you'll be able to manage that with a single kernel invocation. That's kind of like one of the slides that I plan to skip. That's just on the transposes that kind of we did some benchmarking here. All right, so, and we also improved the bandwidth calculations within all CUDA models. So essentially, before that, it was all the hard-coded. So now, when you want to do the copy, we do the path planning for you. We decided which channels are the best. It was also based on on the fixed bandwidth. Now we're using an email essentially to more accurately estimate the bandwidth profiles for you on the underlying GPU system, and basically help to be able to pick up the fastest paths available when you move your data. And I think that's it with the section. So I just want to close it with the robustness. So I think it was the most boring section from this talk, in my opinion, but I think also fairly important. So there's a few things that we do in this direction right now, and that's kind of what I want to talk to you about now. So we added integration to the GTS framework, and now basically when you're adding new features, so actual writing code for Realm, you can actually write the unit tests. So we also integrated with the CI. And so far we got from 0 to roughly 23-25% with all outstanding PRs so coverage. So we covered some of the DMA channels, event subsystems like barriers, completion queues, general events. We covered some of the runtime independent data structures, utility functions. There's a long way to go. It's also usually involves a lot of refactoring where you have to make sure that the code is unit testable, doesn't have runtime dependency on any singleton objects and everything. But our objective is to be able to actually reach the 60%. So, and also, for example, to improve the quality, for example, when you push the PRs, to be able to actually require that there is at least 70-80% coverage on the new code that's being pushed. So, yeah, that's the unit tests. Now, I think Wei was also driving the effort to add the regression tests for Realm. So we designed and wrote a set of benchmarks, like, for the battery, subgraph, active messages, general matrix multiply, and also work with the automation team to set up the continuous monitoring. So basically, when you have a UI, so that will look like this, where on a continuous basis, you can just pull up these graphs and see if there's any offending change that basically introduces a regression in your code. So hopefully that kind of, allows to detect some of the things early. So, and basically like, not only increase the quality, but actually to maintain the quality of the runtime that we have today. Right. So, and last but not least, I just want to kind of have this slide a standalone realm. So basically for us, objective is we sort of want to become slightly more independent and slightly have a little bit more visibility. So kind of like, the goal would be to have more direct customers, have more diversity. So that'll help us to be able to improve the pressure on our system to perform and do well. And basically, hopefully bring new features and just to help us to evolve as a product overall in a good way. So I think we will have this discussion for today later. So I'm personally looking forward to it. Okay. Yeah, and that's kind of like the last slide. So I think I'm done with this. There are a lot of features that are left out. So if there's something you actually wanted to hear, did not. So I apologize for that. I'm definitely myself or like a way Corey would be more than happy to actually take all the questions offline. There's a lot of things we want to talk about. So a lot of things we plan to do. So, and I think with this talk, I think personally for me, is the most objective is not to tell you what we have done, but actually to hear about what you think we should have been doing, should have done, and maybe have some suggestions on how to actually evolve us as a product in general. So thank you. I think that'll be all.